Okay, let's start. It's always very exciting to start a new year of research at TTIC, but today, I'm really happy because I get to be the first person in the world ever to introduce TTIC Emeritus Professor. I mean, really a worldwide honor. Let me introduce to you Emeritus Professor David McAllester. And he's going to talk to us about the modest topic of reasoning and mathematics.
About 2009, I started giving talks about a Moore's law of AI. We were doing computer vision and we were seeing significant advances every year. And I don't want to quantify significant, but for many years, in teaching deep learning, I would spend the whole first lecture convincing people that we were seeing this Moore's law of AI. I don't do that anymore because it's now obvious. I mean, everybody believes that there's this rapid advance. So this is not just significant, but I think the word dramatic has become appropriate. So here's what's happened in automated theorem proving between July 2024 in July 2025. So in July 2024, Google DeepMind got a silver medal at the IMO, the International Mathematics Olympiad, but they used weeks of compute, so it wasn't really real time. And they solved two or three of the problems with a geometry solver. That was this very fancy algorithm that solved geometry problems. All right, 1 year later, both Gemini and ChatGPT got gold medals with no tool use. They're not calling a geometry theorem prover. They're not calling lean. Done completely in natural language by the language models, and they got gold medals. Then just this past month, both Gemini and GPT achieved competed in the International Collegiate Programming Contest and solved, in the Gemini's case, 10 out of 12, in GPT's case, 12 out of 12. And that GPT surpassed all human teams. But again, I think they were using a lot of time. So I'm like an old theorem proving guy, and a lot of people, when they retire, they return to their roots. So I'm sort of returning to my roots these days, but these results raise a question. Has formal logic become irrelevant? And I think a more natural question for a lot of people here, if you're in AI, is, was formal logic ever relevant? It was this big thing in the 60s and was generally viewed as a failure from an AI point of view. So let me just say a few things in defense of formal logic. So compilers and type checking remain fundamental to training models and even inference time running models that generate code. Right? So programming is a case where formal reasoning, formal logic still seems to be fundamental to compilers. And compilers are important in AI as training. Another point to be made is that natural language proofs, whether they're done by people or by a language model, right? So language models are solving these IMO problems in language and being evaluated by their English solutions. But natural language proofs apparently are unreliable. Certainly human proofs are unreliable. So a lot of people believe that a significant fraction, something like half, of published theorems in mathematics are actually not proven. The proofs are incorrect. So there is a lot of interest right now by prominent mathematicians, including Terence Tao, in formally verifying mathematics, pushing it through a formal verifier, this system called lean in particular. And there's another point that I like to make frequently, which is that I can't believe that logic is irrelevant simply because logic seems so transparently present in human language. Human language has tree structure, it appears to be. Logic was developed originally as a model of human language. You go back to the 19th century roots. So there seems to be something significant. There may be something important about logic in finding the next transformer or some kind of other deep learning architecture. Okay. I also want to point out these three cultures. So the three cultures I'm talking about are mathematicians, AI researchers, and programming language developers. Are there any programming language people in the audience? Okay. we all write programs. These days, most PhDs in mathematics and AI never study logic. They never take a course in first order logic or set theory. I think that's true even of mathematics. Do we have any mathematics grad students? Have you taken a course in foundations? One has and one hasn't. Two have? Okay. Not all of them. If you're in programming languages, programming language people are trained in some form of logic. Okay, so I thought I'd make a list of formal logic systems, together with software that's been built to use these systems. Now, I'm sure you're all really anxious to dive into the details of all of the structure of all of these systems, which I'm not going to do right away. But I just wanted to make a list to point out that there's first order predicate calculus, there's higher order logic, there's a Mello-Frankel set theory. That is taken by mathematicians to be the foundation of mathematics, ZFC. And then there's dependent type theory, lean. Lean is the thing that Terence Tao is using to verify mathematics, and that's based on a different foundation. That's based on a type theoretic foundation. Okay, the main point of this talk is going to be that type theory wins. So that's the main takeaway. And I'm going to try to explain why. Why is type theory so much better than ZFC? And I think it's going to be interesting. Really, the reason is that it's not just, you had to add one word to type theory, call it dependent type theory. And dependent type theory is the formalism that gives you the proper treatment of the concept of isomorphism. What I'm going to argue is that the concept of isomorphism is really, really fundamental to the structure of mathematics. But we all program, and programming is sort of a program is written in a formal language. It has all the aspects of formal logic, right? So it provides a nice metaphor that we all understand, and I'm going to use it as a metaphor for isomorphism. So in particular, I want to talk about object-oriented programming, like objects in Python, right? You have object-oriented programming. The programmer defines the user interface, what methods are available to the user, and then they provide an implementation. And the implementation is supposed to be hidden from the user. I can implement priority queues in different ways, in such a way that the user interface behaves identically. And the idea is that this notion of an implementation in a user interface is the fundamental phenomenon of isomorphism. So let's break that down a little bit. Let's talk about translating programming into mathematics. So mathematicians use the word representation rather than implementation. A group, probably most of you know what a group is. A group is a set of elements together with a group operation, combines two elements, inverse operation, identity element. That definition of a group is a kind of user interface. But then you get these representation theorems. So Cayley's theorem says you take an arbitrary group defined with this user interface, and every arbitrary group is isomorphic, whatever that means, isomorphic to a group whose elements are permutations and whose group operation is composition. And so that's a statement about the possible representation of a certain user interface. So that should be sense. Please interrupt and ask questions.
Sorry, so
At will. Good.
So just to say again what you said, like if you give me like a specific group, the analogy that you're drawing is like that group is like a particular like function, like a function that I would see in Python that I don't know how I don't know the definition of the function, but I know its inputs and outputs. Is that right?
So if somebody gives you a group as an object, right, you can determine how many elements there are, maybe. I mean, you should be able to. If it's a finite group, you can apply the operator, but you can't see how that element is implemented.
Gotcha. So determining the number of elements of the group is like I can evaluate a particular function that's exposed to me.
So in mathematics, to be isomorphic, you'd have to have the same number of members. I'm not sure exactly what Python interface would let you ask how many members there are, but in mathematics, to be isomorphic means you have the same number of members.
Gotcha.
So I could say, let X be a member, let Y be a member. Can they be different?
Yeah.
And I could count how many members there are. So we have this notion of isomorphism and this notion of representation. Okay, now I'm going to get creepy. There are things that creep me out, sort of philosophical things that creep me out. And one is this title that gets quoted all the time about the unreasonable effectiveness of mathematics and physical sciences. This is a Wigner, it was a paper that Wigner wrote, and this was the title of the paper. And why is this true? Or what does it mean? So let's do some examples. So physical space. We're living in a physical space, right? And this physical space can be represented, or it's called R3. It's a three-dimensional vector space. Why is our three-dimensional vector space so clearly mathematical? I'll just go through these examples, and then I want to discuss this in more detail. Riemannian manifolds. You don't have to know what that is, but it was developed by Riemann in 1827. It's fundamental to gravitation 100 years later. Lie groups and Lie algebras, developed in the 1870s, are fundamental to particle physics.
Actually, curious. I mean, are you implying here, or is it true that Descartes developed R3 not thinking about a physical space, or was
that was another direction,
right?
Nonetheless,
okay.
It is a fundamental. A vector space is a fundamental concept of mathematics.
But in that case, it was the physical world.
In that case, supposedly he was looking at a fly on the ceiling and realizing he could count tiles. Okay, so the idea is, I want to go back to this first example of a vector space, right? So our physical space, we can talk about when two vectors are orthogonal. It's actually an inner product space. And so that inner product is part of the user interface of an inner product space, but it's not part of the user interface of an arbitrary vector space. An arbitrary vector space does not have that inner product, and it changes what you can say. It also, if you don't have the inner product, it is true that every three-dimensional vector space, any two of them are isomorphic. Any two three-dimensional vector spaces are isomorphic. You take a vector space and you take its dual, which is the set of linear functions on the vector space, and they are isomorphic because they're both three-dimensional, but there's no natural or canonical isomorphism. Now, these are real theorems. To say that there's no natural isomorphism is a real theorem. How do we treat these kinds of theorems that talk about isomorphism rigorously? You can't really do it in ZFC. ZFC exposes all the implementation all the way down. Like number 2 is like the set containing 0 and the set containing 1. So it's really important. These interfaces are really important, and I want to argue that it's this conceptual structure, and the conceptual structure is based on the interfaces. What does it mean to be a vector space? It's that user interface, and together with the properties. So what's really what's really happening in this unreasonable effectiveness in the physical sciences is not the effectiveness of ZFC, it's the effectiveness of these concepts that are based on these abstractions. So you could rephrase it, I would rephrase it as the unreasonable effectiveness of isomorphism, of this idea that we can identify objects. And it's actually done recursively. So the real numbers, how do we formalize the real numbers? If you pick up a book on real analysis, there's sort of two ways to go. You can axiomatize it. You can write down properties of the real numbers. And then you prove as a theorem that any two models of those axioms are isomorphic, modulo this interface to the real numbers. It specifies the real numbers up to isomorphism. In particular, any set bounded below has a greatest lower bound. So the real numbers themselves are something defined by an interface. You can also implement them. You can implement them as Dedekind cuts or Cauchy sequences. But we still say the real numbers, and we do this all the time. We'll say the graph, the complete graph on 5 elements. So we'll use a definite noun phrase to describe a particular structure up to isomorphism. So I said this was creepy. Is God is God a mathematician? Why does this work so well? And I think physicists really are a little struck by this. Okay, here's another thing that creeps me out. So the first thing that creeps me out is the unreasonable effectiveness of isomorphism in understanding the world. Here's another thing that creeps me out, is Platonism. In what sense are the theorems of mathematics actually true? Right? Do the objects of mathematics actually exist? Certainly mathematicians will talk about the sphere. Right? The sphere can be represented as the set of triples of numbers with norm 1. Right? That represents the sphere. But the sphere is this abstract manifold, topological space or something. And this seems related to the idea that mathematics is true. What does it mean when you say that mathematics it really is true, right? That the sphere is this compact two-manifold. How can you say that it's really true unless there are things that we're talking about that have properties that really are there? And what's creepy about this, Platonism, okay, let me back up a little bit. Roger Penrose, famous physicist, right? Roger Penrose wrote a book called The Emperor's New Mind, in which he espoused the belief that mathematicians like him have direct access to truth. And because they have direct access to truth, we can't be a machine. Because machines provably, because we have Gödel's incompleteness theorem, right? And machines can't have access to truth, right? So we can't be a machine. So the Emperor's New Mind. It's crazy. I'm an AI person, we are machines. But the statement that we are a machine interacts with this Platonic idea. Before I go there, let me go to the next slide. Another aspect of Platonism is things like Gödel's incompleteness theorem. I talk about the foundations, people always raise Gödel's incompleteness theorems. So Gödel's incompleteness theorem would say there exist true statements of arithmetic. Basic statements about the numbers that are true but can never be proved. If you fix a sound system, whatever your sound system is, like ZFC or dependent type theory, there's always sound. What does sound mean? It means it can only prove true things. Everything it proves is true. There exists something that's true that can't be proved. So if we are machines, why do we have this intuition about truth? Right? How did Gödel define truth? Right? It turns out that there is a mathematical definition of truth. And also, if people are Platonists, right? Some people are more Platon. There's this professor at Harvard, Hugh Wooden, who is an extreme Platonist. I believe in truth about the numbers, but I'm not sure about the continuum hypothesis. If people are machines, and people can be Platonists, then machines can be Platonists. Right? A machine should have all of these same thoughts, all of these same theorems that we have, including Gödel's incompleteness theorem and the recognition that there are true things that can't be proved. So Platonist machines are possible. But it still doesn't really explain why these particular statements, these particular consequences of ZFC or dependent type theory, we believe are really true. And that gets at a sort of a psychological question.
So you said that people are machines and people can have truth values. That does not imply that machines can have truth values. It implies some machines can have truth values.
That's what I meant. There exists some
machines that can have, okay. That's an important distinction, right? I mean,
Sorry,
this does not have truth. Anyway.
okay, right, okay. Good.
what do you refer to as truth? Because eventually whatever you have is your representation of what is something else. And it's eventually your representation.
So if I write down, the formula for all x, for all numbers n, there exists a number greater than. You can write that formula. I'm not sure, and that formula would be a representation of a statement. Is that what you're getting at? So I've got this formula that's a representation of a statement. And then when Gödel defines truth, he cheats, right? He says, for all x, phi of x, for all x, there exists a y greater than x. Is true if, goddammit, for all x, there exists a y that's greater than x.
So it's kind of like a loop, right?
Well, except that second statement feels like it's saying something that has a truth value. If you just say it informally, if you don't refer to the formula, you just make the statement about the numbers. It feels like you're defining what that formula means. You can define, I call it denotational semantics. You can define the meaning of the formula. The meaning of a formula is either true or false. It's a nice closed form. Okay, so, but if we're machines and we believe that there's this philosophical question: would Martian mathematics be the same as human mathematics? Right? There's an independently evolved species. It's got maybe an independently evolved axiomatic system. Maybe its truths are different from ours. But we certainly believe our truths, right? 'Cause by definition. So where does mathematics come from, and why do we believe it's objectively true if we're just born as some kind of machine? So that gets related to the question of why is it so natural? Why is isomorphism so natural? Mathematicians just adopt it without making a big deal out of it. If we talk about graphs, right? If I talk about two graphs being isomorphic, it means that there's a bijection between their nodes that identifies their edges. People just, get it. And you can sort of argue that isomorphism is an ideal case of metaphor or analogy. These two things are the same, metaphorical. Psychologists who talk about metaphor will talk about the old model of the atom where the electron is orbiting in planetary systems. And that's really an isomorphism. But they talk about it as if it's an analogy. So, it feels like it may be related to Chomsky's notion of a language faculty. Right? Maybe there's no language faculty, but maybe there's a reasoning faculty. And I think minimalism, Chomsky sort of moved in that direction. And I don't want to make a big deal out of that. It's just an idea, right? That somehow, and that might suggest that understanding this is relevant to AI. Well, if there's a reasoning faculty, it'd be nice to, if it's related to analogy, it might suggest a different deep learning architecture. as some kind of analogy mechanism. Yeah.
Are you viewing reasoning as kind of inherently related to language, or can there be a notion of reasoning without language?
That's a tough question. I seem to remember every high school student asked themselves that question.
Didn't find the answer
Is
yet.
thought in language? Certainly, even if every thought is rendered as language, large language models don't compute that way, right? They compute with neural networks and they produce a sentence. Okay, type theory wins. This is I'm going to try to explain why type theory wins. So it took a surprisingly long time. So type theory was evolving as part of computer science. Computer science programs naturally have types. You start out with floats and ints, and they get much more sophisticated. Type theory evolved. It eventually developed into or produced something called Martin-Löf type theory, which is a form of dependent type theory. I'll explain what I mean by dependent type theory later. But it took a surprisingly long time, 1995, as these things go, is pretty late, to realize that these dependent type systems had the property that you could interpret each type in a dependent type system as a groupoid. What does that mean? It means that each type is a type. It has a set of things in it, right? They're instances of the type. And you can interpret a type as a set of things such that any two of them are isomorphic. That's what a groupoid means. It means a category, a set of things in a set of morphisms. And a groupoid has the property that every morphism is an isomorphism. So equality in dependent type theory can be interpreted as isomorphism. And that's natural because we often talk about the complete group or the reals or the integers, right? And what we're really talking about is some kind of isomorphism class. So there was a paper in 1995 that proved this. So let me break this down a little bit. So types. So an arrow type is a function type. So what I've written here on the first line is f is a function from a type sigma to a type tau. And suppose I have two things of type sigma, S1 and S2, two instances of sigma. And think of these as objects. All right, so f is going to take an object in the class sigma and produce an object in the class tau. And I've got two objects in the class sigma, and I apply f to them. And if they're equal as sigma, and now we're going to interpret equal as sigma as isomorphic. Okay, so these things, so now we're interpreting equality, we're reinterpreting equality in dependent type theory as isomorphism. And you get this substitution of isomorphics. If S1 and S2 are isomorphic in sigma, then when I apply F, they're isomorphic in tau. And this is something that is sort of built into mathematical understanding. We just naturally adopt this substitution property. But it's fundamentally, the point here is that it's fundamentally type theoretical. Okay, so let me back up a little bit. So there's this weird, I'm claiming the unreasonable effectiveness of mathematics and the physical sciences is really an unreasonable effectiveness of isomorphism in these abstract objects, classes that are defined up to isomorphism. Isomorphism is a type theoretic, I'm claiming. Isomorphism itself is a type theoretic phenomenon. The type system is going to guarantee that the user respects the user's interface. That's the type system's job. So that's saying that type theory has this unreasonable effectiveness in the physical sciences. At least you could sort of push in that direction, which is that's getting stranger, I think. Okay. Now I'm probably going to ask you to bear with me and actually go through some logic. I'm going to try to describe what is dependent type theory. So I've sort of said what it does, right? The dependent type theory is going to allow you to define these concepts, these types, these classes, and it's going to provide a notion of user interface, and it's going to, and the type system is going to guarantee that the user doesn't violate the interface. Now this dependent type theory has two origins. Actually, it really has just the first origin, and I've worked out the second origin. So the first origin is simply the evolution of type systems for programming languages. So the type systems for programming languages eventually descended on dependent type theory. And this has aspects that drive me crazy. I can yell at people over this. I have yelled at people over these aspects of type theory. It's a proof theoretic approach. They don't emphasize truth and compositional semantics because they get into trouble if they do that. So it's a proof theoretic approach. It treats propositions as types. This is the thing that really drives me crazy. So they represent a proposition as a type. And it's true if that type is inhabited, meaning there exists an instance of it. There exists a program of that type. And the program of that type is interpreted as a proof that the type is inhabited. So a proof, a proposition is a type, a proof is a lambda term that's in that type. Drives me crazy. It does not naturally yield the excluded middle, so you don't naturally get from this that either P or not P. And you can give plenty of examples of obviously true statements that really rely on P or not P. Okay, but so what I'm going to talk about here is another way of deriving dependent type theory that just starts from first order predicate calculus. This first order predicate calculus was the thing that came out of an attempt to model language. Right? So it's much more directly a model of human language. If you do it this way, you define things model theoretically. That's getting back to this idea of, for all x something, the formula for all x something means for all x something. So that's kind of model theoretic, assigning meaning to the expressions. It treats propositions as Booleans, so every proposition, every closed proposition is going to be either true or false. And it seems a better fit to the way people think. Also, equality is treated as primitive. There's this bizarre treatment of equality. Martin Law type theory. Okay, so I'm retiring. And part of the reason I wanted to retire was to focus on this stuff. So I've started a company called Platonics. I like Platonism. And it's also a sort of in-your-face response to the programming language approach. Platonism. The inference system is going to be called CURT after Gödel. The true constructivists hate Gödel. But the real advantage is not so much this difference in origins. I'm thinking of CURT is based on just generalizing first order logic. The real difference is going to be in the algorithms, which it's a company, it's going to be proprietary. Okay, I'm actually almost done. So what I'm going to do now is go through, I haven't really said what dependent type theory is. So I'm going to define dependent type theory. I'm going to derive it from first order logic. Okay, so how many people have ever gone through any first order logic? Excellent. So in first order logic, we have function symbols and we have predicate symbols and we have constants. Right? And you can have these well-formed expressions. So you can apply a predicate symbol to some number of arguments. The number of arguments has to match the number of arguments that predicate symbol takes. You can apply a function symbol to arguments. The number of arguments has to match the number of arguments that function symbol takes. You have constants, you have equality, quantifiers. the point I'm making is that there's a notion of a well-formed expression in first-order logic. Every application has to have the right number of arguments. Very simple, right? So, and the set of constants and function symbols are called the signature of the language. They determine what the well-formed formulas are, right? What's your set of constants and predicates? Now, we can go to multi-sorted first-order logic. This is a kind of trivial extension. All I'm going to do is make distinction between sorts. So I might have a graph, and the graph might have nodes and it might have colors. Right, and those are two different sorts. And now every function symbol is going to take arguments, but for every argument you have to say what sort it's in. Right, so I can have something that takes a node and gives you back a color. So color of would take a node going to a color. And so now the signature is a little richer because you have sorts. And the function and the statements of the types of the function symbols involve those sorts. Multi-sorted higher order logic. So in higher order logic, you can have constants that take as arguments functions or predicates. So something can take a function as an argument. And the set of types, so in multi-sorted first order logic, you have the sorts are the types. Right now we're going to have a grammar of types. Right, so we're going to have this space of types. And the space of types can be written as this grammar. So a type is either a sort, like node or color. Those would be types. We have some set of sorts as types. Bool we'll have as a type. And then for any two types, we'll have the type of pairs of a tau1 and a tau2. So we'll have pair types. We'll also have function types. This grammar of types is called simple types. And there's something called simply typed lambda calculus, which is like this. I have a book by Bob Carpenter called Typological Semantics of English. So I've talked about this relationship between language and logic. And the first chapter of that book is simply typed lambda calculus, even though it's a book on natural language. So these are the simple types.
So, I mean, you're not allowing literals here or constants. Like, I cannot have something type
I haven't written down the well-formed expressions. The well-formed expressions would include variables of each type.
But even for types, like for
We
example,
have sorts. Sorts are your base constants, like node, color.
are the natural numbers a sort or is a set a sort? Because if I want to have something like, for example, I want to talk about a sequence, I need to talk about
The natural numbers would be a tuple of the sort number and the operator plus. So the natural numbers you can define as, let's say the natural numbers are a set of naturals.
I want to define a sequence. Because I define a sequence as mapping from the natural numbers to a set, right?
You can't, sequence is not.
Or a sequence is not a type.
It's not a simple type.
Oh, that's simple type. I say, okay.
These are the simple types. Okay. Okay, so now we make the big jump. It's not actually that big a jump. So the big jump to dependent type theory is almost trivial. I'm going to replace this pair type, this cross, with a dependent pair type. So this is the dependent pair type. So this says, this is the type of pairs, it's a type of pairs, such that the first element of the pair has type tau, and the second element of the pair is of a type that depends on the value of the first element. So I could have a type, say, of a number and a number greater than that number. So that's what makes it a dependent type. And I should just, if I stop right there, I can point out that I can define, let's say the natural numbers, the type of the natural numbers. And let's say the natural numbers consist of the set of numbers in the successor function. Right? That's enough to define the natural numbers. We've got a unique element that has no predecessor, and then we've got this successor function. So the type of the natural numbers would be a pair, this pair, of the type, the sort n, the type of that is the sort, and the successor function where the type of the successor function is defined in terms of the sort that is the first element. Apologies for the technical mumbo jumbo. But that's the essence of dependent type theory. The really important thing in dependent type theory is a pair whose first element is the sort. Right? So you have a sort, and then you have this successor function. And isomorphism is going to be based on bijections between sorts. So two implementations of the natural numbers are identical if there's a bijection between the two sets of numbers. A graph would be a set of nodes together with more structures. Two graphs are isomorphic if there's a bijection between the two sets of nodes. Okay, so that's dependent pair type. And that's going to give us a lot of structures. This is a dependent function type. This is going to be a function, an element of this type. This is replacing arrow. An element of this type is a function that takes an input of type tau and produces an output whose type depends on the type tau. And in Kurt's version of dependent type theory, I also have restriction types. This is going to be the type of elements of tau that satisfy some formula. So I can add axioms. I can define natural numbers and add axioms. If there were any programming, there are no programming language people here. If there were, this slide would be down. There's something called polymorphism. So if you wanted to find a generic composition operator, you wanted to find one that takes the three, it's going to compose two functions. There are three domains involved. Two domains of the first function, the function that takes that value and produces another one. So you could write a compose, but you have to first specify the three sorts or domains involved. Now, since I'm into this, in Lean, another thing that drives me crazy, in Lean they have this infinite stack of universals. In mathematics, we have set. Mathematicians are happy with, for the most part, with set. Occasionally you need a class if you want to do category theory, but you don't need an infinite stack. So Kurt's going to have set and class. Okay, takeaways, and then I'm done. I'm happy to have questions. First point, formal methods seem likely to remain relevant. Isomorphism is central to the structure of mathematics. It's fundamental to empirical, and the structure of mathematics is fundamental to empirical physics, and possibly manifest in some innate human reasoning faculty. I don't know what to make of that. Isomorphism is type theoretic, based on these, it's defined in terms of type theoretic constraints, and dependent type theory you don't have to go with this constructive propositions as type stuff. You can just get it straight from first order logic. Okay, so that's all I have to say. Happy to take questions.
We have lots of time for questions, and if other people that are speaking this year would also leave so much time for questions, I think that's great. So, myself. Yeah.
To what extent do you think the formalism is restricted to formal math? So I can imagine the type you can regard like facts in the real world and even some pieces of data as similarly as just analogous to propositions in formal math. Is that? I mean, does it have any prospects at all?
I have a cognitive psychologist friend who has no training in. She's not a STEM person. I try to explain this stuff to her. She's a cognitive psychologist, so she's very familiar with the word concept. There's lots of psychological literature on what it means to be a concept. And there's this idea of a prototype. So what I could interpret your question as saying, is whatever the linguistic notion or cognitive notion of concept, is that, how strong is the analogy between that and the mathematics notion of type built here? Is that?
No, exactly. I think it's like if you instead of just regarding formal formal propositions in mathematics, informal mathematics as types, you can, I truly imagine you can also regard like propositions about things happening in real world, like some real information and even some data, some numerical data, also as some types. Is there any hard limitations on?
Well, I'm just trying to think on my feet, but consider the word bus. Words and verbs have restrictions. So I can say, I rode the bus, but I wouldn't say I wrote the bus. I could say I wrote a book. So it's clear that semantic, like the semantics of that category is influencing the context in which it can appear. So maybe that's still not answering your question. I interpret your question as to what extent is this generalized to language?
To natural language, instead of just formal.
Right. So natural language does seem to have these semantic constraints on the constructions.
Oh no, I was just following up because I feel like what you said earlier about isomorphism is exactly what philosophers write in the book called The Metaphors We Live By. So I think that could be an answer to his question in terms of metaphors as literally isomorphisms in the structure of Lakoff, yes, exactly.
So, two questions. One is, I'm curious, so you suggest you're a very different approach than the approach taken by Lean. It's not so different?
Their approach rubs me the wrong way. I get very agitated about it. But you can translate.
I see. So any algorithm you can do in your system, you can also do in their system and vice versa? I see. So what algorithms you use is kind of independent of which, how you choose to...
There are consequences. Like you have to do special things with the excluded middle, and you can do it. You can take any proof in one and translate it to a proof in the other. But my opinion is the proofs become harder to find in one formalism versus the other.
The second question is, you talked about you justified the need for formal methods in AI by wanting to have formal proofs for mathematical theorems.
That was one.
Okay, but let's focus on that. Suppose I accept the need for having formal proofs for math. Why does that have to be part of the AI or learning system as opposed to external to it? It's just something we produce in the same way that we produce, a text answer. We also, so for us, you can ask, like, do we as humans are able to produce a formal Lean proof? Okay? But that doesn't mean that we have the Lean prover inside our machine. So why does the Lean prover have to be part of the AI as opposed to just something that the outputs do? In the same way, if you ask these programming competitions, you ask to produce a Python or whatever, they produce a program, but they don't necessarily. They probably do actually have something inside for verification, but they don't necessarily have to have the programming language as part of the system.
So the top level motivation you're focusing on is say, I take a mathematics paper and I want to make sure that the theorems are actually proved.
No, or you ask me to prove, you ask the system to prove something, and you want to make sure that
the thing I was talking about is just being sure that something is proved.
Yeah, exactly. Yeah.
Right.
But that can be external to the AI system. I don't see why you're arguing. It seems to be two orthogonal.
Well, the point I was making was that the certainty is going to come from logic, from symbolic computation. That's the only point I'm making.
But it doesn't mean that the AI system has to have logic inside.
AI,
the machine, whatever you're learning.
Well, there's CURT, right? CURT is just like it's analogous.
That's an external, right? The question is, should GPT incorporate Lean or CURT into it?
That's a different question.
Okay, I thought that was what you're getting at. Okay, so you're not taking a position on that here.
I'm not taking a position on that. Presumably the analogy I make is that the language model is analogous to the person. it's thinking in English, probably can make mistakes, just like the person can make mistakes. And then you could try to drive.
So formal methods could still be relevant for AI.
For at least for being certain about.
Irrelevant.
Well, it depends what you mean by AI.
Right. Like there are many attempts of incorporating dependent types into programming languages. But indeed, it is very difficult for compilers to make inferences regarding them because there are plenty of undecidable problems in that. It's not as simple as checking the consistency of more traditional types. So like what can we really achieve like with those systems? Like is there sort of, still like a limit in terms of, what can be inferred?
So Lean is a programming language. And I was talking to some Lean people, and I pointed out that, for example, to really prove that a program's correct, you probably want to prove that it terminates. And termination is undecidable. So they have a way of just saying, of not requiring the compiler to prove termination. But if you're doing mathematics, so I'm not trying to build a programming language. I'm trying to do mathematics. And when you do mathematics and you write some statement, mathematicians want to check that it's meaningful. And so however the types are defined, a mathematician is going to stop if that thing looks like it's nonsensical. And nonsensical means it typically means the types are violated somehow. And the type, I was talking to Jeremy Avogad at some point and saying that I had these restriction types. These restriction types are immediately uncheckable. They're immediately undecidable, whether something's in this restriction type. And he just said, you just made type checking undecidable, and he just dismissed it. But mathematicians do this, right? And they check those types. So, you could say, proving things is impossible, so we should never, is undecidable, whether it's a theorem, so we should never try to prove. So yes, what you're saying is true, but I'm not going to try to build a programming language.
Questions?
Just curious on your take on. So I think of maybe isomorphism as related to equalities, and in mathematics there are also lots of interesting inequalities where you can relate things which are on the face of it not connected. Going through isomorphism, are you saying every inequality has to come from some equality? Like, can I know that set A is bigger than B without finding an embedding of A inside B? Sorry, A is smaller than B without finding an embedding. All right, more generally, how do you think of inequalities like this?
I'm not sure exactly how to interpret. There's what you might call disequality, which is two things are not equal, which is not the order.
Mm-hmm.
And there, when I took topology, you want to prove theorems about. So a fundamental thing you want to do in mathematics is classification. You define a concept like topological space, and you want to say what spaces are there, and that question is always up to isomorphism. And I remember. My professor in topology saying, what we're going to do is we're going to define the homotopy group. And if two things have different homotopy groups, different as groups, then they're not isomorphic. And he never pointed out that isomorphism has this substitution property, which he's using right there, right? Because if they were isomorphic, they would have to have the same, and that's that substitution property. Isomorphism is very useful in proving disequalities. Now, this question about, is A less than B, does that require demonstrating an injection? Right? Obviously, we compute with numbers, because we don't demonstrate injections when we prove this number is less than that number. So, you're free to use all the tools of mathematics in whatever you're proving. I mean, it sort of sounds like a constructivist, right?
Okay.
Maybe we should let
Okay,
people go.
so yeah, let's thank David again.